afternoon. My name is Augustine Effiong, and today I'll be presenting my final term presentation for the Mine 5025, the Advanced Mining Design class. The presentation focuses on long-term geomechanical stability and integrity of underground hydrogen storage reservoirs. As hydrogen becomes more important for the energy transition, understanding how reservoirs behave mechanically over years of cyclic injection and production is critical, because geomechanical integrity determines whether a reservoir can safely and repeatedly store hydrogen without inducing fractures, fault slipping, excessive subsidence, or cap rock failure. This is because hydrogen, as we know, is highly mobile and has different mechanical implications than conventional gas storage. Therefore, a rigorous assessment is required. What can be expected in this presentation would be me beginning with a brief overview of hydrogen storage in depleted reservoirs. Then I'll introduce fundamental poroelastic concepts needed to understand stress-pressure coupling. Next, I'll walk us through numerical modeling results, including injection, shutting, and production cycles. Finally, I'll discuss implications for reservoir stability and long-term operational integrity. With that, let's get started on the learning objectives. So before we dive into the technical part of this material, I want to outline what students should take away from this lecture. So firstly, students should understand why hydrogen storage is important in this emerging technology. So we'll highlight the operational and safety motivations for ensuring geomechanical stability throughout cyclic injection and withdrawal. Next, we'll distinguish between drained and undrained poroelastic behavior, because this understanding is crucial, because pore pressure changes during injection and production, which strongly were coupled with rock deformation. Students would also learn about the Mandel's problem, a classic poromechanics benchmark. It will illustrate how pressure, diffusion, and deformation interact, including the counterintuitive Mandelsera effect. We'll then transition from a theory to application by examining results from a 3D poroelastic reservoir. The goal here is to connect numerical predictions to real field skill geomechanical behavior. And finally, students should be able to link poroelastic mechanisms to long-term risk in hydrogen storage, such as stress cycling, compaction, uplift, and potential failure. So with this objective in mind, let us start by framing the importance of hydrogen storage and why geomechanics becomes central. So UHS, as it's widely known, is becoming a key component of the future low-carbon energy systems. As renewable energy demands increases, as such, there is a need to store excess energy at large scales and over a long period in time. But what then is hydrogen storage, underground hydrogen storage? Here, the basic concepts is that during periods when renewable energy is abundant, such as days where you have windy and sunny days, hydrogen can be produced and injected into deep geological formations. This stored hydrogen can then be withdrawn for later purposes during high demand periods, such as the winter, in which the hydrogen withdrawal is used for power generation or industrial applications. And this gives us a way to balance the grid and smooth out intermittency of renewables. But then, why is it important? Why store hydrogen underground? There are several reasons why underground storage is attractive. First of all, it's because the subsurface provides enormous season scale storage capacity, far more better than batteries or above ground tanks. Secondly, hydrogen storage plays an important role in stabilizing grid with high level of wind and solar energy. Also, the storage sites may operate with multiple injection and withdrawal cycles per year. This means that the reservoir is repeatedly pressured and depressurized. And finally, these pressure fluctuations are significant, thereby they are large enough to alter mechanical behavior of the storage formation or the surrounding cap rock. In this figure here, which I got from the work of Wan et al. In 2024, the schematic illustrates a general idea where excess electrical energy is used to compress gas and inject into a depleted oil and gas reservoir, which you can see in this part of the figure. So the subsurface then acts as a storage container, and the gas is later brought back to the surface and converted into electricity when needed. It is worth pointing out that while this illustration uses compressed air, the same concepts apply directly to hydrogen storage. And this leads me to the key point of today's lecture. These cyclic pressure swings cause stress redistribution and deformation in the reservoir and the cap rock. So understanding how these stresses evolve and whether the system remains mechanically stable over the years of operation requires poroelastic analysis, which I'm going to discuss in subsequent slides. This motivates the next section, where we would build on the fundamentals of poroelasticity and connect them to both the Mandel's problem and our 3D reservoir simulation. So now that we have seen what UHS looks like, it is important to understand why geomechanics play such a central role in evaluating storage performance and safety. So the figure there, which I got from ChatGPT, it's not very beautiful. But then it shows that when hydrogen is injected, which you see in the first panel of the figure, the reservoir pressure increases, which you can see in the orange colors. We see an increase in reservoir pressure. Also, according to effective stress principles, a higher pore pressure reduces effective stress carried by the rock skeleton, which you can see that effective stress is reduced. And this can bring the reservoir or cap rock closer to a mechanical failure. During the shut-in period, pressure redistributes through diffusion, which you can see there is a kind of like a circle there, so it's moving towards equilibrium. However, during the production phases, when we depressurize the reservoir, we see pressure reduces, thereby causing pore pressure to fall, causing the effective stress in return to rise. These cycles repeat many times per year because stresses and deformation accumulate over long periods. Cyclic operations therefore can cause mechanical fatigue, uplift or subsidence at the surface, permeability changes, or even fault reactivation. So the key message here is that the mechanical behavior of the reservoir depends not on pressure, but how pressure changes over with time. This motivates the need for poroelastic analysis, which couples pressure and deformation. That's what we'll begin to explore next by going to the fundamentals of poroelasticity in the next slide. So now let's walk through the fundamentals of poroelasticity, the central concept that links fluid pressure and rock deformation. So what poroelasticity means is that it describes how stress in porous rock is shared between the solid skeleton and the pore fluid. At any time the pore pressure changes, the effective stress carried by the rock frame also changes. That is a key coupling here. So, stress is usually partitioned, where you have the total stress is divided between the solid skeleton, which carries effective stress, and also the pore fluid, which carries the pore pressure. So according to Biott's effective stress law, we can express the relationship as that effective stress is the difference between the total stress and the pore pressure. This equation actually tells us how pore pressure affects mechanical stress. So intuitively, when pore pressure increases, effective stress decreases, which is what you see there. That means the rock carries more load. That means the rock softens. But when pore pressure decreases, effective stresses now begin to increase. What that means is that the rock carries more burden. This behavior actually governs reservoir compaction, uplift, and the risk of shear failure or fault activation. So why does pore elasticity matter for reservoirs? This coupling is absolutely central during, for instance, underground hydrogen storage, where we inject, shorten, and produce repeatedly. These cycles cause some kind of stress redistribution, strain accumulation, changes in fracture permeability, and long-term deformation of the reservoir and cap rock. So now let's take a look at a practical example following the reason used by Mark Zuckerberg to understand how pore pressure changes directly with horizontal stresses. So if you look at the figure we have on the slide, let's imagine a laterally extensive reservoir, something like 5 to 10 times wider than its thickness. This kind of reservoir is typical in the field, otherwise the reservoir would not be economically efficient. So as you can see in the figure, you have the overburden, which applies vertical stress. And when we change pore pressure, for instance, during production of hydrocarbons, the horizontal stresses respond accordingly. So we can solve this elastically by looking at how the change in horizontal stress depends on two important material parameters, one of which is the Poisson's ratio, V, which controls lateral strain under vertical loading. The second one is the Biott's coefficient, which is called alpha, which describes how compliant the rock frame is. The physical meaning of these parameters are that the Biott's coefficient, which is the alpha, ranges from 0 to 1. That is, in solid or weak rocks, alpha is equal to 1 because the grains are stiff, but the grain framework is compliant. However, in stiff or cemented rocks, alpha is usually less than 1 because the rock frame carries more of the load. So alpha tells us how strongly pore pressure affects the effective stresses. And this is consistent with Terzaghi's effective stress law from the 1930s. But in rocks, we generalize it with the Biott's coefficient alpha. So in poroelastic simulations, which we would see in the subsequent slides, alpha is a required input, also as well as the Poisson's ratio. So for soft and porous rocks, we often assume that alpha is equal to 1 and the Poisson ratio V is around 0.25 or 0.30. These are, of course, reasonable values for sedimentary rocks such as sandstones. So using these values, we can plug it in where we have V is equal to 0.25 and alpha is equal to 1. This becomes A, this number, the value we get out of that result is usually called the stress path, which tells us how much the horizontal stress is changed per unit pore pressure. So if we look at the results, we would see that if you plug those values in, we see that the horizontal stress is changed by 2/3 of the pore pressure change. In this case, the vertical stresses do not change, so only the horizontal stresses respond to the applied force. So a practical example would be that if the pore pressure decreases by, say, 6,000 psi, then the horizontal stresses would decrease by 2/3 of 6,000, which is 4,000 psi. So this simple but powerful relationship between pore pressure and stress is the foundation of understanding reservoir deformation, fracture reactivation and compaction, and caprock behavior. We would move on to the next slide where we would see how to visualize these changes in the actual reservoir. So moving on, now that we've reviewed how pore pressure couples with stress through pore elasticity, we can build a framework we'll use to interpret all of our simulation results in the subsequent slides. So to understand whether the reservoir deforms, weakens, or approaches failure, we would use what is called the Mohr cycle, which is a representation of the stress states. As this Mohr cycle or the diagram allows us to see directly how the changes in pore pressure and poroelastic stresses influence fault stability, or maybe the caprock integrity of the reservoir in question. So let's begin. We can see a cylinder which represents a rock element under in situ stresses, where sigma 1 is the axial or vertical load from the overburden and sigma 3 is the confining horizontal stress. A fault cuts through these elements at some angle, where we have the pore pressure, which is PF, acting normal to the fault plane and reduces effective normal stress, which is given by the equation you can see on the slide. So when pore pressure increases, we can see the normal stress decreases. So that means the fault becomes weaker and the shear stress tau required to slip to the floor, the shear stress tau required to slip the fault becomes smaller. So on the right side now of the slide, which you can see is the Mohr cycle. Those different three semicycles you see on the figure in figure 5, which I would want to mention at this point that I found this image figure 4 and figure 5 interesting from Matthew Acosta's presentation in the last 3 weeks. Yeah, it was very intuitive and very self-explanatory. So now let's look at how this appears on the Mohr cycle. So every fault orientation corresponds to a point on the Mohr cycle with the coordinates sigma n, which is the effective normal stress on the horizontal side of the plot, and then tau, which is the shear stress acting on the fault on the vertical side of the plot. So when the pore pressure increases, the entire Mohr cycle shifts from right to left. This is because the effective normal stresses decrease everywhere, as we did see in the equation on the left hand side of the plot. This shift alone moves the fault point closer to failure because it reduces the resistance to shear But it's worth noting that pore pressure causes more than just a shift from right to left through pore elastic deformation. It also changes the sigma 1 and sigma 3 themselves. That is why the red circle is larger. Its radius increases because the difference between sigma 1 and sigma 3 grows. Also, on the plot in figure 5, you see a straight line which cuts on the vertical side of the plot, which is called the failure envelope. And the actual name is actually the Morse column failure envelope, defined by cohesion C and the friction, which is represented by mu. So when the Morse circle touches that envelope, the rock has reached its shear strength and fault reactivation occurs. Also similar for when we are going to see in our reservoir simulation results, if we see that some of those more envelopes approach that more column failure, we know that the rock is about to fail. So I noted this part, which you can see at the bottom, that the C and that's the cohesion and the friction angle depend on rock properties, which can be obtained from experimental data from the lab or literature values for different rock types. So in the next couple of slides, we are going to move into the actual purpose of this lecture, which would involve the Mandel's problem and also our reservoir simulation results. So now that we've built the physical intuition of how pore pressure couples with stress and how that affects failure through the Morse cycle, I wanted to introduce the Mandel's problem, which is a classical benchmark for testing whether a simulator can correctly capture those pore elastic interactions. And it's worthy to note that this benchmark will form the conceptual foundation for interpreting our hydrogen storage results in the subsequent slides. So the first question would be, why do we need the Mandel's problem? So Mandel's problem is important because it is the simplest geometry where fluid pressure and mechanical deformations are fully coupled. Other classical models do not capture this coupling, such as the dry linear elasticity, where there is no pore fluid, so deformation is purely mechanical. Also, in the Terzaghi consolidation, pore pressure evolves by diffusion, but mechanical stresses do not feed back into the pressure field. So neither of these physics do we need. However, the Mandel's problem introduces full coupling. Pore pressure effects on deformation. Deformation feeds back into pressure. And all together, they produce a non-monotonic pore pressure evolution known as the Mandel-Syra effect. This is one of the signature behaviors of pore elasticity in reservoir formations. This problem also serves as a benchmark test for pore elastic simulators such as MRST, which is what we use in the simulation in this study. So if a simulator cannot reproduce the Mandel-Syra effect or behavior, it cannot correctly simulate coupled pressure-stress interactions in a real reservoir. So, what is the physical meaning? The Mandel's problem shows that even if we load the rock instantaneously, the pressure may first increase, then decrease. Then again, increase in certain regions. This monotonic response is exactly the kind of behavior we see in reservoirs during injection, shutting, and production. So the geometry which you see in figure 14.6, sorry, that's supposed to be figure 7, which I got from the work of Anderson in 2021, shows a rectangular slab compressed between two rigid impermeable plates with width 2 times the length and the height is equal to h. So it's infinite in the z direction. So right after the load is applied, fluid can escape through the lateral boundaries. This other parts, the lateral boundaries, that's in the x direction. And that would be either the plus or minus L direction. The result is a lateral pressure gradient and deformation pattern that evolves with time. Some key assumptions of the Mandel's model are that it is a fully saturated poroelastic material, instantaneous load is applied, drain sides where fluid exists, impermeable top and bottom. So we have rigid plates on the top and bottom. So we have a plane strain conditions too. And these assumptions make the solution analytically solvable and ideal for validating simulations. I've also listed the table. You can see the table 1 shows the boundary conditions applied in the Mandel's problem, which I have mentioned already. So importantly, this benchmark is important because the same mechanisms occur in hydrogen storage reservoirs as I mentioned earlier. That when we change pore pressure during injection, we see the effective stresses go down, and also when we shorten, it creates some kind of pressure redistribution. Also, when we deplete or depressurize the reservoir, it induces a non-uniform effective stress changes. So the Mandel solution would help us understand and interpret those results, which we would see. Okay, so now that we've introduced the Mandel's problem as a classical benchmark for coupled poroelasticity, let's break down two extreme responses it predicts. The first being the undrained response, which occurs immediately after loading, and then the drain response, which represents a long-term equilibrium. So we can see for undrained conditions T at 0, right after the load is applied, we have what is called an undrained response. In this regime, there is no drainage because the fluid has no time to move. As such, pore pressure rises uniformly and carries most of the load. As a result, effective stress is small because, like we said in previous discussions, that effective stress equals to the total stress minus the pore pressure. So that means the material behaves stiffly, meaning a very little settlement occurs. So mathematically, we can say that this corresponds to a no flow boundary condition, or simply insufficient time for diffusion to occur, since the diffusion is too long compared to the time since loading. So one thing I would want to highlight is the Skempton's coefficient, which is equal to 1. And what this means is that almost the entire load is initially taken by the pore pressure, exactly what we expect for an undrained condition. So we say that the storage term dominates this particular phase of the simulation. So now moving to the drained response, where we say the dimensionless time is almost infinity. We have that after enough time has passed, all the fluid has drained to the boundaries. So in this drained response, we have that pore pressure drops to 0 everywhere because literally all the fluid has escaped. We also have that effective stress carries the load since pore pressure is 0. So the material undergoes some kind of a maximum settlement, reaching a long-term drain value. As well, we can also say that mathematically this occurs when diffusion time is large, enough that pressure equilibrates across the medium. And in this case, Skempton's coefficient B is equal to 0, meaning there is no pressure buildup. The rock frame carries the load entirely, and we can say this is no more a storage dominated region. So in figure 7, you're now looking at the special grid which we used in MRST to implement the Mandel's problem, which is a rectangular domain 10 meters wide and 1 meter high. I discretized it into a fine mesh to actually and accurately capture both the short-term on-drain response and long-term response. So this is the actual grid used in our simulation, and in the next slide we'll look at the results to see these responses as they develop in practice. So on this slide I'm showing numerical results of a Mandel problem simulated in the MATLAB reservoir simulation toolbox. So these plots illustrate how material transition from an on-drain response immediately after loading to a drained response as pore fluid diffuses out of the domain. I'll try to walk us through each figure, try to explain the axis and highlight the physics behind the result. So on figure 8, which we have a displacement versus dimensionless time, right on the x-axis we have the dimensionless time normalized by a characteristic drainage time, where that means that if you have a smaller t, or tau in this case, it means a very early on-drain response, and a larger t means a long-term drain response. And on the y-axis we have vertical displacement at the top, which we can say uy. So a more negative value of the displacement equals to a more settlement. So if we look at the figure, you can see that at early times when t is near 0, settlement is negligible. This is because the pore fluid is carrying most of the load. As such, the material is effectively stiff under on-drain conditions as we had mentioned before. But if you look at it as we go from left to right on the x-axis, you see time increases. So we see pore pressure begins to dissipate, meaning effective stresses increase, causing the slab to settle more. Where at the largest tau, which is 2, we see that the curve has reached the drain settlement, representing the final deformation once all the pore pressure has dissipated. So in the next figure, which you can see, I'm showing the center pore pressure versus dimensionless time. Again, the x-axis, which we can see there, still represents dimensionless time scale. Then on the y-axis, we represent a normalized pore pressure at the center of the slab. So values near 1 equates to a higher pore pressure, which is the on-drain condition, and values near 0 are the drain conditions, which we have pore pressure approaching 0. So if we look at the figure at t close to 0, we see pore pressure at the center exhibits a sharp jump to a high value. This is a classic on-drain response, and something which is embedded in the Minder-Seira effect, that the fluid has no time to move, so pressure builds up instantly. But as time progresses through the x-axis, as we can see, the pressure gradually decreases. I'm sorry, the highlighter is not really showing. You see, as we move down towards the right, we see the pressure gradually decays as fluid diffuses towards the drain boundary. When this normalized pressure approaches 0, the system must have reached the drained state, meaning that fluid pressure has fully dissipated. So I'm also showing the spatial pressure profiles in figure 10. Here on my x-axis, I'm showing a normalized horizontal distance, while on my y-axis, I'm showing a normalized pore pressure. So this particular plot shows how pore pressure varies spatially across the slab at different times of the simulation. So as we can see in the legend, as tau equals 0.01, which is the first one here, which I would say that's a cyan color, you see pressure is nearly uniform, which is exactly what we expect from an undrained condition. But as T increases, pressure near the drain boundary drops, first creating something like a pressure gradient, and these gradients become stronger over time, reflecting diffusion of fluid towards the boundary. But at the highest, I'm sorry about that. At the highest time, which is 2, we see pore pressure is almost 0 on the y-axis, everywhere indicating that fluid has reached the drained condition. Also, I'm showing here a 2D pressure contour snapshot, where you have on the x-axis, I'm showing the length ranging from 0 to 10 meters, and on the y, which is the height, representing 0 to 1 meter. We also have a color bar which is showing us the fluid pressure changes at different points in the slab. So the yellow color, which you can see towards the left boundary is higher, represents a higher pressure, which is the undrained condition. The middle is the partially drained, and the blue parts or the lighter purple part shows the drained condition. This contour plot gives I would say, if you will, a special snapshot of the pressure field. Areas in yellow represent regions where pressure is still high, meaning the fluid has not yet drained, but the purple sides of the bound of the figure shows the right boundary where pressure is 0. So the gradual change in color represents diffusion fronts, the fluid diffusion fronts moving across the slab as pore pressure redistributes. So bearing this in mind, as we have done this validated the undrained to drain transition using the Mandel's benchmark, we can sort of apply this understanding to our hydrogen storage reservoir simulation, where similar pore elastic effects occur during injection shorting and drawdown cycles, which we are going to build from this intuition in subsequent slides. So now that we've validated the poroelastic behavior using the Mandel problem, as we saw in the last slide, I would like to move into the full 3D reservoir model, which is oftentimes used in simulating hydrogen storage. This slide would summarize the model's geometry, boundary conditions, and the MRST model. MRST in this case is the MATLAB reservoir simulation tool. The models used to couple fluid flow and geomechanics. So first, the model geometry and grid. A reservoir is represented using a Cartesian 20 by 20 by 5 grid, as you can see in figure 12. Physically, this corresponds to a 2000 meters by 2000 meter area and a 50 meters thick reservoir subdivided into 5 vertical layers. Each is approximately 100 by 100 by 10, which provides a balance between numerical resolution and computational cost. We also include a single central vertical well that penetrates all through the 5 layers, which you can see in figure 12 in the red and red alignments there. So on table 2, we see the rock and mechanical properties, where we have permeability to be 100 millidarcy is also uniform. We can say it's a homogeneous reservoir. Porosity 2 is also homogeneous at 0.25. We have the Young modulus 1 gigapascal, which means the rock is soft and unconsolidated. Poisson's ratio about 0.3, typically saturated rock, and the Buert's coefficient at 1, which is a fully compliant rock. Moving on to the mechanical boundary conditions. So you can see the bottom is fixed, meaning we have a zero displacement. All other boundaries apply a confining traction equal to the far-field reservoir pressure, approximately 200 bar. We also turn on gravity so that the reservoir experiences real in situ stresses. For the flow boundary conditions, the model is set up as a closed reservoir where all boundaries are no flow except the well. This means the well is the only inject and outlet for the injected or produced gas. Also, there is no lateral drainage, which is consistent with an isolated storage structure. So in terms of well and operation strategy, the well is operated in a bottom hole pressure control mode. During injection, we set a high bottom hole pressure equals to the reference pressure plus 250 bars. During production, we lower the BHP to the reference pressure minus 200 bar to simulate aggressive drawdown. Each storage cycle lasts about 360 days, broken into 4 months of injection, 4 months of shutting, and 4 months of production. We simulate 5 full cycles with 10 days time step to capture pressure stresses and deformation evolution. So to solve the problem, we use the ATmechanics model in MRST, which is coupled with the Make Black Oil model. This adds several capabilities such as the nonlinear finite element star poroelasticity, displacements unknowns, which is the U. We also have a fully coupled geomechanical formulation. Also has a correct stress transfer and deformation, and dynamic updates of porosity and permeability if that option is selected or chosen. For the Make Black Oil model, it specifically couples the black oil multiphase flow with linear elasticity under the Buert's poroelasticity. This ensures that pore pressure and stress evolve simultaneously, and the mechanical deformation feedbacks into flow, as well as capturing uplift, compaction, and stress cycle, all essential processes during underground hydrogen storage. In short, I would say this exactly is what the Mandel problem teaches, but is now implemented in a full 3D reservoir with a real well. But before moving into the simulation results, I would want to briefly explain the motivation behind this model and what we aim to study. The idea is to take the Mandel type poroelastic behavior which we validated and translate it into a realistic 3D reservoir with a well, as this model allows us to examine the same coupled pressure stress mechanism but now under cyclic hydrogen storage operation. Specifically, we want to understand how pore pressure near the well builds up during injection, redistributes during a shortened period, and relaxes during production. Also, how effective stresses and deformation evolve, including the risk of shear failure, which we would assess through the use of the Moore column, compaction, or uplift. Also, how the BHP well pressure and flow rates reflect the poroelastic response of the reservoir. In other words, this model provides a bridge between the Mandel benchmark and the long-term geomechanical stability of an underground hydrogen storage site. So with this in mind, let us now look at the results and see how these poroelastic effects unfold over the storage cycles. So now that we've discussed the geometry and the model setup, we want to walk you through the numerical response of the reservoir over the 5 injection, shut-in, and production cycles, where in the results I'm going to show that some of the plots would capture some different aspects of poroelastic behavior. But I want to begin with well performance, which you can see in figure 13, before going into the interpretation of the mechanical results, which we would see subsequently. So on the top left here, you can see on the y-axis we have rates in cubic meters, and on the x-axis we have time in days up to 1,800 days. So the blue curve represents injection and the red curve represents production, which you can see clearly the repeated pattern where injection gives a gradual increase, a gradual rate increase, where production gives a sharp negative rate response, which you can see in this sinusoidal form. And so this confirms that the well is responding exactly to the BHP, the bottom hole pressure schedule we imposed. On the second, the middle plot, which you can see on the left, we have the y-axis, which is pressure in bar, and on the x-axis again we have time in days. So the black curve which we see in the middle figure represents the bottom hole pressure which we imposed, ranging from about 200 bar during production and about 400 to 500 bars during injection. While the dashed green lines which you see, there's other green lines here which you see, represents the well block pressure. The pressure, that is the pressure in the reservoir cell connected to the well. So we notice that the well block pressure lags behind the bottom hole pressure, and this is a poroelastic response that the rock stores part of the pressure changes as deformation before the pore fluid fully equilibrates. And on the last plot in that slab, we have cumulative injection and production rates. Again, the y-axis shows the cumulative volume in cubic meters. Over time, we see the cumulative injection is consistently higher than the cumulative production, which is something we expect in a gas storage system where permeability and porosity have a part to play. We also have things like gas compressibility, which causes an incomplete recovery. Aside from that, poroelastic expansion also absorbs part of the injected volume. As you see, pressure does not return to the baseline in each cycle. This leads to a slight long-term pressure buildup in the reservoir. So in figure 16, I'm showing the evolution of total stress over time. Time again is in days. which is in the x-axis, and the y-axis is the mean total stress in megapascal. So we use a sign convention which is negative to represent compression and tension to represent positive. So the points above 0, as we can see in this figure, the point above 0 represents tension, and the points below in the negative represents compression. So let's start with that of the well cell, which is the blue color which you see here. So in the legend you can see we have well cell, mid cell, and far field cell. So the blue color in the figure represents the well cell. So we see that that well cell experiences the most intense pressure changes. During injection, we see the stress moves up from about -7 megapascal, which was compression, up to towards +12 to +13 megapascal, which you can see in that slight increase there. You can see that. So this happens because pore pressure increases as we inject, and at this point effective stresses collapses. So we can say that the rock is driven towards tension in this case. And during the shutting period, which you see is this kind of descent, or this slope which you see here, so the stress drop back sharply because there is some kind of redistribution of stresses and some kind of equilibration which we see there. The pore pressure at this point diffuses away from the well, which leads us to the production stage, which is the lower part of the blue curve for the first cycle. We see a deep negative drop in stress reaching to about -9 MPa, because the pore pressure at this point is drawn down, and we know effective stresses increase. And when we have an effective stress increase, we have that the reservoir becomes compacted. So this pattern repeats for all the cycles with a slightly increasing tension, and also we have the compression for the production part. So for the mid cell, which is the orange curve which you have there, the one that slightly looks like the one in the well cell, is also, in this case, is farther away from the pressure source. It shows the same general pattern, but with a much smaller magnitude. We see slight movement towards tension during injection, mid relaxation during shutting, and we see a moderate compression during production, also reflecting some kind of poroelastic response. But the most interesting one is the far cell, which is the yellow color, which I wanted to highlight clearly. So the far field response is very smooth, almost sinusoidal, but importantly it shows a gradual upward drift across the cycles. But the question would be, why does this happen, even though the far field is far from the well and small amounts of pore pressure diffuse outwards each cell cycle and accumulate? So we need to understand that the boundary conditions and asymmetric loading also cause some slight residual deformation after each cycle, which we can see in that ratcheting effect which we see, and is perfectly consistent with the poroelastic theory. Also in figure 15 I put up volumetric strain, which in the x-axis again we see time in days, and the y-axis is volumetric strain, where a positive volumetric strain would represent dilation or expansion, where we see an increase in the pore volume, which leads to the swelling, and the negative volumetric strain represents compaction. So again, in the well cell, we see during injection, the volumetric strain increases up to about 0.016, indicating a strong dilation as the reservoir lifts and expands radially. During shorting, the volumetric strain collapses into the negative values, not quite closely, but it also shows us what we saw in the stresses. And during production, we see the compaction deepens further as the pressure drops. So the well cell therefore undergoes the strongest and dilation compaction cycles. So for the mid cell in orange, we see a moderate dilation and compaction, but smoother behavior, while in the far field cell, we see a smaller amplitude, but again we see the same slight upward drift caused by poroelastic memory and pressure diffusion. In the figure 16, I'm showing a maximum displacement versus time. Again, time is in days in the x-axis, and the y-axis shows a vertical displacement in meters. So in the figure 16, we see a clear uplift during injection, reaching about 1.0 to 1.05 meters of displacement. During production, displacement sharply drops to around 0.3 meters, which you can see in this first cycle and second cycle. We see in the last cycle, we see that the displacement drops to almost about 0.25 meters. So this uplift settlement pattern repeats cyclically, confirming a strong poroelastic coupling. So over the 5 cycles, we see a peak displacement slowly increases, again due to incomplete pressure recovery and cumulative reservoir expansion. So the key observations of the numerical simulation is what you see there, but I'm not going to spend time reading that. But it is important to note that the reservoir shows a classic poroelastic cycling. Dilation during injection, we have compaction during production, and a stress hysteresis across the cycles. But to assess failure risk, we need to interpret these stresses on this stress part on a Morse cycle, which I had introduced in the earlier part of my presentation, because this will allow us to see whether injection pushes the rock towards tension or whether production drives it closer to shear failure. That we cannot categorically say because of the figures I have shown. So next I will show how pore pressure cycling shifts stress states on a Moore diagram, and we would see the failure criteria which we are going to use to assess these results. So on this slide, I'm using the Morse cycle to examine shear and tensile failure risk at key stages of the injection, shorting, and production cycle. So each of the rows would correspond to cycle 1 and cycle 5, with each column corresponding to injection, shorting, and production, where the top panel would show the full stress range and the lower panel zooms in around the actual reservoir stresses. So in figure 17, which you can see the x-axis, we plot effective normal stresses where compression is negative, as it appears there in both of the plots, while on the right hand side we plot tau. So the values range from 0 to 0 megapascal on the right to about minus 45 on the left, on the far left. And while the vertical axis plots, which you see here, we're plotting shear stress tau, which is around 5 to 6 megapascal depending on the stage. The radius of each of the cycle will represent the deviatoric or shear loading at the time. So I wanted to make a technical clarification here about this red line which we see here, which is the Moore column failure envelope, which is shown here. It's not plotted in its original or in its correct orientation. A properly implemented Moore column slopes upward from left to right, but because of the constraints before this presentation deadline, I wasn't able to fully correct the plotting code. However, the principal stresses which I'm presenting on this slide and the Moore circles themselves are correct. So I would say only the envelope is misdrawn. And even when plotted correctly, the envelope would still lie far above the circles. None of the conclusions on the mechanical stability here would change. So let us take a look at figure 17 closely. So we see during the first injection cycle, all the Moore circles shift from left to right, meaning the effective stresses become less compressive as pressure builds up. So the well cell, which is represented in the blue here, is the largest circle. It experiences the largest shift. I'm sorry about that. The circle spans roughly from minus 40 megapascal to minus 28 megapascal in the effective normal stresses. So this particular result matches what we saw earlier, where we have a large dilation and a movement towards tension during injection. And as you can see in the zoomed panel, it makes it clear all the circles remain far above or far below the correct failure envelope. So figure 18 there shows the shorting cycle results for the first cycle. So at the shorting, we see pore pressure begins to diffuse outwards. So the circles shift leftward, indicating a return towards compression. Here the radius also becomes smaller because the deviatoric stress is relaxed. Again, as we can see, none of these circles reach the Moore column failure envelope. So moving forward to the production stage in this first cycle, we see that during production we have a reduction in pore pressure, so effective stress is increased, so the circles shift. So in this case, the circles are shifting from left to right, which means we are going into a stronger compression area. It's consistent with the compaction which we saw earlier in the volumetric strain and displacement plots. Even with this increase in compression, all circles remain safely below the shear failure line. So now I'm showing the results for the Moore circle at the final cycle, which is cycle 5, which we see that by the cycle 5 the same patterns repeat, but slightly we have a cumulative change. We see that for the far field and the mid cell circles, the moves are comparably similar to what we had in cycle 1. So this again reflects that poroelastic ratcheting which we discussed earlier, where some pressure increments diffuse outward and accumulate over a long-term cycling. So again, despite these cycles, as we can see, they still remain below the failure envelope. So for the shorting and production, which we see, the shorting in cycle 5 shows a mild leftward shift as pressure redistributes, and production shows the strongest compression of the entire cycle. So if the zoom panel show that by the end of cycle 5, stresses among the mid and far field cells have become homogenized so due to repeated cycling. But importantly, I would want to mention that even in the end of cycle 5, when the compression, as we can see, is at its peak, right, the system has accumulated deformation across 5 complete cycles. The Morse cycle still does not get above the failure envelope, still stay closely below the failure envelope. So overall, the Morse cycles here, which I have shown in this slide, may show that the reservoir experiences strong cyclic stress swings near the well, and also none of these stresses at any stage or any cycle approach shear or tensile failure. So we can say that the system remains mechanically stable throughout. However, these Morse cycles only show stresses states at 3 special cells. And I wanted us to see that for us to really understand the spatial distribution of stress and strain and how deformation evolves cell by cell across the 3D reservoir, we would now look at the full spatial stress and strain column maps on the next slide. And so as we looked at the stress evolution at the individual cells using Morse cycle, this particular slide, we'll begin to see how the stresses and strain are distributed spatially across the entire reservoir. So the contour map which you see in this figure which I'm showing here comes from a horizontal slice through the reservoir. So remember, our reservoir had 5 layers, so K is equal to 3, so that means we are the third layer, which is the middle depth of the model. So on the left of each of the pairs which we are going to see on the left hand side here, the left hand side, we have, for the first one, we have the mean effective stresses in megapascal. So compression is negative, so the darker blues indicate a stronger compression, while yellows indicate a reduced compression. So for the other figure which shows strain, we have volumetric strain as epsilon v here. So the positive values which you see represent dilation or expansion, while the negative indicates compaction. I just wanted to put that out before I show the remaining results. So looking at figure 23, which is the first injection cycle, we see a strong reduction in compression right around the well, as you can see here. So the center becomes less compressive, around minus 30 megapascal, compared to the far field, which stays close to minus 36 MPa. So again, this matches exactly what we saw in the Morse cycles during injection, and the cycle shifted to the right, meaning effective stress became less compressive and moved closer to tensile conditions. So on the strain map, which we see here on this other side, this strain map confirms that we get a clear dilation zone around the well, which you can see with the more yellow values, where epsilon v reaching about plus 0.015. If you look at the color scale there, you would see that it's around 0.15. So the same dilation we saw earlier in the time series plots, we can see it here in the spatial stress strain maps. So moving on, figure 24, which you can see, the figure on the left hand side of figure 24 shows again the mean effective stresses, and on the right we see volumetric strain against time. So during shortened period, pore pressure begins to diffuse outward, which I have explained already, and you can see the stress field becomes uniform. Look at that, all of that, it becomes almost uniform. So the near well region is slightly less compressive than the outer reservoir, which you can see here. The strong dilation which we saw during injection, we don't see it in this case, which is also equivalent to what we saw in the Morse cycle. So moving on now to the production, which is figure 25. We see that production gives us an opposite behavior from the injection. If you look at all of that, you see it gives us an opposite behavior. So we know as pore pressure drops, the effective stress begins to increase. So you can see a strong compression zone around the well, where the center now drops to around -29. Look at that for the mean effective stress, which shows that it's more compressive than previous stages. So also the strain field also flips the sign. So instead of dilation here, we have a near well region showing a negative volumetric strain, which you can see here. If you look at the color coding, you will see that this is a minus sign, which indicates compaction. So this matches what we saw, the strongward leftward shift in the Morse cycles we saw during production, where the system moved deeper into compression. So overall, the special maps here confirm exactly the trends we saw in the Morse cycle analysis, where injection reduced compression and increased a strong dilation near the well. For shorting, we have the redistribution and smoothing of the stresses, where production we have a localized compaction and increased compression near the well. So, but it gives this particular slide which I'm showing here gives us a full picture which complements the Morse cycle which I had shown, which were stress state at an individual cell. So, but before we look at the broader implications of this result which we've seen, I would want us to look at the last cycle of production shorting and production and see whether there is any cumulative deformation which evolves after cycling this reservoir for 5 cycles. So in this case, this is a figure 28. So we see that at the end of the 5th injection phase, we see the same pattern in cycle 1, but now it's slightly more pronounced. If you look at this, you see the color coding is more pronounced, but I wouldn't want us to spend more time here because I'm going to do like a comparative analysis so you can see the difference between cycle 1 and cycle 5. So I'm just going to run through and show you the figures here. And so we've confirmed how these stresses and strain evolve, especially at the final cycle. But again, let's move on and compare the initial cycle and the final cycle so that we'll be able to make some conclusions and also give some implications and control on how to understand these results. So here I want to compare excuse me, how the special distribution of stress and strain evolves from the 1st cycle to the 5th cycle. So these maps show a horizontal slice again, which I say k is equal to 3, and the axis span the full 2-kilometer reservoir in both x and y. So let's look at the figure on the left hand side, which the row above it is the 1st cycle and the row below it. So here is the 1st cycle and here is the final cycle. So starting with the injection phase on the left hand side of the map, so in both cycles we see injection reduces compression around the well from -35 megapascal down to -30 to 32 megapascal. But what is important here is the magnitude. and the pattern are almost identical in cycle 1 and cycle 5. The zone of reduced compression does not expand or intensify over the cycles, which also mirrors what we saw in the Mohr cycles, which we showed from cycle 1 and 5. So meaning there is no progressive movement towards tension or failure. And looking at the volumetric strain, so this is your volumetric strain, the one on the right. So I'm sorry, I think I messed it up. So the figure on the left shows the first injection cycle, and the figure on the right shows the fifth injection and production cycle. Yeah, I'm sorry about that. So the one on the top here shows that. So we see that this is production, these are your production, and these are your injections. So for the volumetric strain, likewise the dilation around the wall remains stable across the cycles in both the first and the last cycle. But here the volumetric strain peaks from 0.15 to about 0.16. So if you look at the color coding, here is in the final cycle, you see there is some kind of peak here as opposed to this one, and you can see also on the sides of the reservoir you see some peaks around there. So it shows the strong dilation, but it is completely repeatable. The rock expands during injection, returns during production. It shows no sign of cumulative damage. And likewise production on the right here, where we have cycle 1 and cycle 5, we see that during production the near well region becomes most compressed. You see minus 24 to minus 26 megapascal in both cycles. What we see here is very consistent because the amplitude of the compression is same in cycle 1 and 5, and the spatial footprint does not enlarge. They are almost similar. So the Mohr cycle, which we discussed earlier, corroborated this. So the production cycles shift left into compression, but cycle 5 still looks like cycle 1, so there is no ratcheting towards shear failure. Same with the volumetric strain, we just see an increase from 0.03 to about 0.0 minus 0.04 here. So we can say it's more pronounced here as it is up here. So if we move mid-field and far-field evolution, we see that around 500 to 700 meters, we do see a light trend across cycles. Compression reduces by 1 megapascal. Dilation increases slightly from plus 0.02 in cycle 1 to about plus 0.013 in cycle 5. So overall, the reservoir here exhibits stable and repeatable poroelastic behavior, large but reversible deformation near the well. We also see an extremely mild long-term ratcheting in the far field and a consistent safe distance from the shear envelope. So now that we've compared how stress and strain behave, especially from the first to the final cycle, the next step will be to interpret what these patterns mean for a long-term reservoir integrity, and the geomechanical limits of cyclic hydrogen storage. So due to the time constraint again and the presentation deadline approaching, I was not able to carry out a full sensitivity analysis or sensitivity studies on injection rate, pressure limits, and number of cycles. But what I've shown here therefore represents one representative operating scenario Under these conditions, the reservoir behaves in a mechanically stable and poroelastic manner, where we see stresses remain compressive, and the Mohs cycle stays away from failure and deformation near the well, and is also very reversible. However, it is important to note that this stability is not unconditional. The results which I have shown in preceding slides clearly show that the near well region experiences the largest stress and strain excursion, and the far field shows a gradual accumulation and deformation over cycles. This means that higher injection rates, larger pressure swings, or long-term cycling could potentially push the system towards excess deformation or failure. So rather than us concluding that the system is always stable, the key implication is that coupled flow geomechanics simulation like this are essential for defining safe operational envelopes, especially for underground hydrogen storage. So for an example problem in this class, we are going to do some kind of stretching from the basic black oil model, which we use to simulate after verifying the Mandel's problem. We would now have to evaluate geomechanical stability of a depleted sandstone reservoir undergoing hydrogen injection and production. So in this case, the reservoir is modeled using a 4-component compositional simulator. So we move from the black oil to the compositional simulator. So we inject gas primarily containing 80% hydrogen, 15% methane, and 5% CO2. And so you would couple, the task is for you to couple a flow model, compositional flow model, couple linear elastic mechanics using the AT mechanics model in MRST. You do stress and strain post-processing, you want to see the result, and also some more cycle interpretation. So you use the boundary conditions I have stated there. We have a fixed bottom. Also, the lateral boundaries are fixed. You use initial uniform in situ stresses. The reservoir properties are given, and the table there, which you can see, would help you understand how many cycles you're supposed to carry out, which is just 2 cycles. So for supplemental materials, I would really advise you go through this the works of Anderson, which gives a brief introduction to poroelasticity and simulation, which would give you a foundation of all the equations you need. Also go to an introduction to reservoir simulation using MATLAB, which is the MRST. And also I want you to watch that YouTube video, which is a presentation given by Mark Zoback in 2022, which will also help you understand what we have been talking about. So this brings me to the end of my presentation, and thank you very much. I would also upload some of those supplementary materials and also this slide for your reference. Thank you very much.